Going around.
Well, sorry for the technical. Today we have a great talk for you about low-level computer vision by on way to compute for scientific. Please welcome Abdulaziz.
Okay. So today I'm going to give a talk about the basic building blocks. So we're not going to get into the high order stuff where you're actually recognizing objects and fingerprint scanning and facial recognition and all that stuff. We're not going to get into today. But we're going to get into the image processing behind the vision. So can anyone tell me give me like a quick definition of what computer vision is and what they think it is? It's computer science, so we don't have any fast and solid definitions.
It's the opposite of computer graphics.
Actually, that's yes. That's quite good.
So,
Anybody else?
We need to also understand concepts from a problem.
That's very good. So with that and the opposite of graphics, I think we have it covered. So one of the definitions is that you're extracting descriptions of the world from pictures or sequences of pictures. So you have normally have a pipeline when it comes to computer vision. You have your images, your image sources, and then you're processing them in some way. And then you're extracting features, and then you're making decisions based on it. So here we have an image of a boat passing under Westminster Bridge. Now, if you look at that, you can tell, maybe you know Westminster Bridge, but you can tell that that's a boat passing under the bridge. And I've told you it's Westminster Bridge. You can see the top colors, and you know that's Westminster Bridge. But how will the computer know that? How many pieces of information does it have to process to be able to tell that that's boat passing under Westminster Bridge? Has to know that that's boat. Has to know that that's Westminster. Has to know what the bridge is. It has to infer that that is passing under the bridge. So there's a lot of information that it has to figure out before it can process this. So what's the big deal? Why is computer vision considered difficult? Why everything that I just said in the previous slide? What makes it such a complicated problem? That's one way. That's one way to do it.
you need to know a lot more details than what can be relayed on a two-dimensional thing,
Exactly.
like the shadows, like the depth.
Okay. Okay, that's part of it. So there are two sides to the problem. It's what's known as an ill-posed problem, which means that you can have one image being produced by completely different objects. So there can be completely different interpretations to the same image. And if we get a chance at the end of the talk, I'll show you some examples of illusions based on this part of the problem, where you look at something and you think it's something, and it turns out it's being created by a completely different. And the other side of the problem is that one object producing many different images. So if I change the lighting, the same face is going to be producing a different image. If I change the angle, the same chair is going to look different. You might want to recognize a category as opposed to a specific object. So how do you get a computer to tell the difference between a calculator and a phone? I mean, these days it's easy with no buttons, but before it was a very difficult problem. Okay. So these are some of the applications we're talking about. make sure that you're following the same object and you don't lose sight, which is completely easy for us to do as human beings, but it's insanely difficult to program. Facial recognition. This one down here is between the self-driving cars and driver assistance. And then we have a bit of design mark detection and landmark recognition. And this one is my favorite, space exploration. It's really useful. This image is from this is a selfie from the Curiosity rover. You see it has two cameras, and this photo worked out awesome. That's because it used some computer vision algorithms to stitch the photo back together from a camera or from multiple images. It uses the cameras to track its path, to decide where it's going, to detect certain rocks that it's looking for that it's interested in for specific. So there it is. Which is why it freaked out about a year ago and it thought it found a piece of metal, but it was just that there was a rock that was shinier than it was supposed to be because it was being hit by the sunlight in a specific way. Even though it was a completely normal rock, the computer vision system on this decided that it was metal. That's what it's for. Okay. We're not going to do any of that cool stuff today. We're going to do the mathematics. We're going to look at the math and the building blocks behind computer vision. Because like I said, you have a pipeline when you're trying to detect objects in an image. You start out with an image source, and then you have to process it in some way so that you can then extract features from it. So today, the three things that we're going to look at are noise reduction, edge detection, and template matching. And luckily for us, they all use the exact same equation. They all use the exact same algorithm. I'm going to show that to you. Okay. We're going to go to a bit of a practical demo. I've set up a big repository. It's a big project. So a virtual environment and install the different. So, and install the files file. You guys want to, because I've set it up as a notebook, so you can go through it at the same time. Before we start this, there's an operator that we have in signal processing and in math. It's a little star. It's an asterisk. Can anybody tell me what it does? Do we have this? It's a joker. It's a joker.
It's a wild card.
It's a wild card. In regular expressions, it's a wild card. In computer science in general, it's a multiplication. In math, it's this thing over here. That star means all of this. Which I'm going to explain without going into the math. And hopefully it'll be easy to follow. Because I promised that I wouldn't go into the details. Okay, so first of all, we're using SciPy here, just purely to grab some images, using NumPy for data structures.
Can you go to what the OpenCV, SimpleCV are?
I'm going to talk about that in the end because everything we're going to do, SimpleCV and OpenCV can do in no time flat. So we're going to do it the hard way, and now, and then I'm not going to show you the library to see it. You'll see that in simplicity it does all the same stuff manual with no plus. But here for now, we're going to do the library using NumPy and then play using Matplotlib. We have happening together. So first, let me explain what this crazy looking equation grid does. So as you know, all images are just pixel map. It's just an array of values. Colored images are 3 to 4 arrays of values. We're going to talk about this base characters. It's just one 2D grid of numbers. So that's what pi is. Pi is just 2D grid of numbers. H is also a 2D grid of numbers, but it's much smaller. So this is what we normally call a filter or mass or kernel. If ever done any processing, you might come across the word kernel. This is what it's a mass. And pi prime over here is just the filter. It's just the result of this equation, which I'm going to show you today.
What you're doing is representing any image as a matrix or as a bitmap of what the values are.
Exactly. I'm converting it into a NumPy array, into just an array of numbers. And what this equation does, because I've written a very, very badly written function here. Never ever do it this way. This is probably the slowest way to do a computation. But what it does is it takes your mask, your kernel, your filter, flips it both ways, flips it upside down and then left to right.
Horizontally.
Yes, horizontally. And then it takes your image and it passes your mask over it. So that's what the estimation is. So every pixel, all we're doing is we're multiplying pixels around it by the mask and summing them together, and that's what that gets us. So we assume everything on the outside is 0. So we have all this sums to 0. 0 times 1, 0. 1, 0, sums to 0. And then to here, we move 1 pixel to the right and do it again. That's an issue. So 6, because that's the value this multiplication is same. We do it one more time. 7 is 2 times 1 is 4. And so on and so forth. So that big equation is essentially just doing this. It's not doing anything else. It's just taking a filter, flipping it, and then passing it over an image. And every time it comes across a pixel, it multiplies pixels around it by the pixel. See that? Sorry.
You can see what it does.
Yes, I actually wrote this to be specifically very, very slow. I actually had to slow it down. That's why you have fast equals so that you can see it running. This is in my Python notebook. For those of you who haven't used it, amazing, amazing tool. You can write these and share them. You'll have instructions. Fantastic. So, the image that I've chosen to do most of the processing tasks on today is Lena, or Lena, depending on that. And she is a staple of the image processing. And this image actually comes standard with SciPy, specifically for image processing. Okay. So this is the image. We've got an image array. This one is VRI in our computer. And then we're going to start trying different filters. So first, I'm going to start with the world's most useless filters, just to demonstrate how these filters look when they're passing across the image. So our first filter,
The original image doesn't have colors.
it does, but I'm using a grayscale version just to simplify it. Okay, so this is our first filter. It's an array of zeros, so 5 by 5 array of zeros. So based on what I showed you over here, can somebody tell me what this filter is going to do to you? If it's all zeros. Exactly. That's why I have very, very subtly named it universal. This is because the filters are also arrays, I can display them as images, but because this is all zeros, it's just black. Now, I run the convolution. You can see that it's very slowly, and you can see the artifact where it's going across the image. It's erasing one block at a time, but because it's sped up a little bit, it's actually erasing one line at a time. So that was what
That's a format.
No, I've slowed it down by a huge amount, just so you can see it in action. In reality, you don't want, you'd actually want to use the convolution function that's inside it. That one works a little bit better.
It's all progressive. It's not.
No, and it could actually do it in and it doesn't need to happen sequentially because you're actually processing based on the original image and creating a third image for that second image. Okay. So this is our second filter. This is just an artifact of the fact that the image is blown up, but essentially it has one pixel in the middle, which is set to white. Everything else is black. So if I run this across the image, what's it doing? It's not going to erase it.
Same thing, because it's just a central pixel. It's value that comes.
Everything around it, the entire neighborhood is multiplied by 0. So you sum it. The only thing that matters is the pixel that it's on. Actually, no, there's a different one. No, with this one, it'll just, this is, like I said, these are the most useless filters in the world, just to demonstrate. This one will just copy the image exactly as it is. Don't change it. So if I run this one, it looks, it's not doing anything, because it's not. It's just scanning on the image without changing. So
Can you explain why it's not doing anything?
like we said in this explanation of convolution, let's say that you're on this pixel over here. Okay, so this is the one that we're trying to process. If everything around here in the filter, in the mask, is 0, then it doesn't matter what it's being multiplied by, it's going to be 0, it's not going to add anything to the sum. The only thing that's going to add something to the sum is a non-zero pixel in the mask. So that one in the middle is just going to sit on the pixel that it's looking at and change it back to itself. So it doesn't do.
Question? What do you do for the edges when they're in the pixel?
Yeah, that's a very good question. There are two methods. One is you either decide to throw away, you don't start at the top, and then you throw away the outer pixels in the image. But then every time you do a convolution, you trim. The other way is the zero padding. So what I'm doing in my convolution function is I'm zero padding. You have to zero pad it by depending on the filter. The filter is 100 by 100, but you need 50 pixels behind it. Yeah, we're going to look at a couple more filters now. Let's see how changing the values here. What it does to the filter.
Allahu Akbar, Allahu Akbar.
So this is all one grid, this abstract mathematics of multiplying it to multiplying this level, but what's the point? Well, one of the first things we can look at is what's known as a mean filter, otherwise known as a low-pass filter, or a smoothing mask, or a blurring mask, or a box mask. This thing is so useful that there are hundreds of words for it. And this is what it looks like. It's pretty boring. But if you notice, these are not zeros, these are not ones, these are, here it's 1 over 25. So we have a 5 by 5 mask, and it's each element of the mask is 1 point. So what this is going to do is as it sits on top of the pixel, it's going to give that pixel the average value of the 25 pixels now, or the 24 pixels now. So it's going to average everything inside the mask and set it to that one. Which is why it's called a mean filter. Exactly. So this will, you should see it start to blur. It doesn't show when it's up here, but as it's progressing down, it starts to start to blur.
Details are fading away.
Exactly. So when it comes to a 2D image, when we're talking about audio, it's easy to think about frequency. If the signal is changing a lot, then it's high frequency. It's changing very, very slowly, it's still frequency. But when it comes to an image, that's a bit more of an obscure concept. Although it's exactly the same thing. So here you have, let's say we're talking about this area over here. You see the change is very, very gradual and very consistent. It's changing from one color to a very similar color over a large space of room. So there's very little change to that. So when you blur it, very little happens. But over here, in this feathers, once again, you should see that that's where the changes are most noticeable. Because this kind of filter will remove out big like quick changes. That's the point. So what it's good for is removing noise. If you have artifacts and noise on the image and you run it through this, it'll smooth out those outcomes. We'll use the edges, but it's also useful. But these filters get very big, very square, and they start to have very weird side effects when you go through it. So instead, we use something called Gaussian filter. And really high intensity in the middle means that anything close to this pixel is really important. Right? Anything far away is not that important. Which means if you, depending on what value you set over here, this changes how wide. So if I open the key, and see it becomes very dynamic. It takes up almost the entire picture like it does.
It's kind of blurred.
Yeah, you might have some of you use Photoshop, some of the filters. One of the most common blurs is the Gaussian blur. That's what this is. This is a Gaussian blur. So if I set this to say 5, you can see this has a much more pronounced blurring effect than the one before.
It's stronger.
And depending on the size of the filter, the blurring will be even more intense because it's taking averages from further away.
When like filters are the same size, like one Gaussian and one mean, in that wouldn't the Gaussian filter be more true to the original image? Because
Yeah.
taking closer.
Exactly. The Gaussian image cares about what's close to the pixel that it's modifying.
So shouldn't it have been like, shouldn't it have resembled the original picture more closely?
No, it depends on what you set some signals. So if I set it now, this will be a less severe. The difference between the averaging filter and Gaussian filter is that this one is smooth, this one has a smoother blur. And it has less of an effect on large areas like this. So the mean filter and the Gaussian filter are what's known as filter. They get big or quick changes. If there are lines where the pixels are one color on one side and there's sudden change, that is the very good the blur and the headline. What we saw happen here. Like I said, the feathers are the ones that are getting the most effective. They change it. But what if you want the opposite? What if you want to highlight the lines and get rid of areas where nothing changes for very long? For that, we have the passive filters for fixing the difference. So this one here, I'm not going to visualize it. So, let's roll with these. First, add up the one. These difference masks add up to 0. It's essentially saying I don't want to change what's happening to me, but it's going to leave somewhere. So here what we're saying is that if there's a change on either side of this pixel, if these two things are not equal on either side of this pixel, then this pixel needs to be more connected. So highlight it more. So if I have a 0 on this side and 1 on this side, then this pixel is going to get twice. If I have exactly the same number on both sides, or very similar numbers on both sides, this pixel is not going to change at all. In fact, it might get switched. It will get switched. If this is a 1 and this is a 1, this will get switched. And because this is looking at horizontal things. So it's only looking at things either side, straight horizontal.
There's the horizontal line is all up.
Actually, you're right, this would be a vertical. This is the vertical. No, the first one. This is if we just change the direction of the filter, so rather than horizontally, we change it to a vertical filter, then it detects lines going the other way, the other direction. Compare this to but notice this hat disappears because it's only in this instance. Some of the feathers are generally not very. You'll notice it looks etched.
Hmm.
And see the difference between these two mirrors. Direction. Here. And you can also check for diagonal. So this is what I was saying earlier by about the position of the numbers in the array. How you create a mask makes a difference to what it's doing. So here, because the -1, 2, -1, and by the way, it doesn't have to be these numbers. It, can be, it doesn't have to be a 3 by 3. It can be a 3.
This is the threshold.
Yeah.
Once you
Yeah, this is just very, very basic, very fine. So -1, if you're going to have a person with an 15, you have to make sure that, let's say you have a line with maybe 15 on either side, you have to make sure that by the time you get to the pixel, everything adds up to 0. So the filter adds up to 0. If you're going to technical edges, that's that. So this one, the difference with technical and the pixel, the change you're looking for is that.
Yeah.
It seems to be a little more pronounced. If you notice there's some lines over here that's more invisible over here. So they're only visible now because
What if some value is negative?
I mean, it will closer to you, but it's not going to be close to detection.
No. As in, you're evaluating the pixel with the filter, and suppose the middle filter is, the middle pixel is very dark, and the side pixel is very bright. So if you go by that filter, the total value, when you sum them up, is going to be negative.
You're multiplying, by the image, you're multiplying only with the 0. So the most it can mean is 1, 1, which is adds up to -2, which is why you want to make sure that the filter itself sums up to 0. It doesn't sum up to it's a -1 because we want the changes on this side of the pixel and the changes on this side of the pixel to have the same width. So if this side of the pixel is different to this side of the pixel, then this will be, the pixel itself will give it more width, will be more pronounced, it will shine brighter on the screen. If they're exactly the same, let's say that this is a bright white dot, and this is a bright white dot, with 1 and 1, this will sum up to -2. And when you add that to whatever's in here, it's going to cancel. It won't change the picture.
Suppose there is an edge, where the middle pixel is 0, the edge pixels are 1 and 1.
Yeah.
Okay, so white, black, white. So the white becomes -1, the middle one becomes 0, this becomes -1, so it's -2. What color is the sun?
Yeah. The array is unsigned because this is a gray scale. So the value would be
0 to 1.
so it's going to be -2 in the unsigned scale. So actually, so 128.
I think possibly,
Okay.
I think possibly here the image is not over to. I'm not sure. I'll check again. With this one, the pixel will get brighter if the diagonal pixels either side of it with each other. How do you make it dark? I'm not sure what the, so you want to instead of right as you get You could do the same thing and then invert it if you wanted to do it. Or you could invert the filter so that it's 1 minus 0.
I think if it's negative, it will be 0.
No, it should be open now. See, there's black pixel in the middle, 2 white pixel in the edges. Okay, so it'll be like -1, 0, -1.
Yeah.
So total is -2. So if I assign this pixel the value of -2 with -2, that doesn't make sense. It should be between 0 and 1.
Yeah, but -2 is represented with binary.
I'm not sure. I'm going to check this again.
For the discussion.
Well, we'll put that, we'll definitely go through that in the discussion. But for now, we don't know. This is what is known as difference mask. And we put it together. So this area over here. It's combining the horizontal, the vertical, and the diagonal. This is what's known as an intersector or a cross filter. But it has issues because it actually focuses on a specific cross. So if you ran this filter on a noisy, it would make the noise, but it would make the noise. So some of the things that you do is that they create a mask where it's on the cross and then the Gaussian filter, so it highlights the lines and then blurs the highlights the this is the detector. It should detect lines in all directions. And it finds highlights and it generally finds quick changes in high frequency changes. So when something changes abruptly, it gets highlighted. So these are the low and high pass filters. Are there any questions before I? This is the last thing that we can do.
One last dumb question.
There are a lot of
If there's a black, does the original color of line matter, or is it just a difference that matters?
yes, it
Just
does.
a difference, right?
I think it might actually make a difference to the original value. Because the original value of the pixel gets multiplied by. I think possibly there was an issue that was happening with my template matching that goes over percentage, which is the value that's it's assigned as negative and then it destroys the entire. There are ways to do that. But yeah, generally the pixel in the middle of the filter does affect the filters. But the color, the original color of the image does not. So if you were to do this on a RGB, you have to run it 3 times, color planes, or you have to create some sort of filter queue that goes through all 3 planes at the same time. And then it would actually, it would make it, there might be lines that, or edges that exist in red, but they don't exist in blue. Or the other way around. So it does make a difference what color you get. It's not just changing it all.
Just to give an example of this, this is a quarter,
Yeah.
and the surrounding ones are half.
Okay.
And this is 1. Another one is like the middle one is half. The surrounding ones are like 1 or 3/4 or something. So the difference is the same, but the original values are different. So will they come out to the same values?
Let's test it out in the discussion. keep a note of these and we'll actually test them out because this is so the in Simple CD, I'm just going to show you the equivalent functions in the actual Simple CD library. Whatever. The last thing that you can do at the low level, or like the most complex thing that you can do at the low level, is to map templates. So, in fact, for a very long time, face detection, face recognition systems were using low level. They didn't have to go to the level where they do facial maps and specific features and find them. They were simply using templates. So when it comes to template mapping, that I'm using the city dot is silhouette to the right. This is the filter. So the filter is now 50 by 50 array of numbers. And when you actually display it, it's a section of the byte. When you involve the array and you filter using this template, what happens is that it brightens up in areas where there's a stronger match to the template. But remember, the template is flipped. You'll notice there are some subtle matches all over the place, but right over here, which is where this template originally came from, right here, there's a bright white color. What it's saying is that that template was found in this right here. Now, when I pulled this image up, I assumed that it was a filter process and Photoshop and it was a silhouette. No, I realized that because when I ran this template, there's a second dot that showed up there, equally bright, which means that this here is actually an exact copy of this one. So I found that out completely by accident while I was using it. That's all I have for the low level. If you guys find this interesting, then maybe at a later date we get some higher level. In template mapping, I just took a section of this image. So this is the icon. The template is this section cut out from the thing. And I just used the combination, same way that I was doing you before with the filters. So I used the template as a filter. So when you do that, the images that match, the pixels that match the brightest are the ones where the filter lines up with.
For example, let's say I have and I want to see it, check whether this has an enemy, not necessarily exactly.
Okay. You can do that. You can definitely do that. But if you want to do that, then you don't have to get into it's known as scale vectors, because this is a single-sized template. So as it passes over the image, it's only going to really detect fields that are the same size as this one. But what you can do is that you can run it multiple times at different sizes. And then that way you make the wheel detector scale variable, which means that it doesn't matter what size wheel it's looking for, as long as it'll match any size wheel, as long as it's placed in the same. You get position variance and lighting variance and all that fantastic stuff. There are many, many ways. But finally, this is raw. This is the raw filtered image with the 3 dots over here. normally what we do with this situation is threshold, so that only pixels higher than a certain threshold will show up. What they get is few very bright dots. And that is smoke. Normally what we do is we find the maximum in the pixel, pixel intensity, minimum pixel intensity, and then some percentage these values. And that's the way it's not make that, but here, deciding if it's 50% higher than every other pixel, then that would show that, otherwise it's black. With any other pixels.
So what's the conclusion from any question? When you start my conclusion, maybe
Yes. At the very, very basic level, in image processing, you are involving filter or an image element. It's at the heart of image processing. And normally what happens is that you'll run a couple of filters in your pipeline, and then from the results of those filters, you'll run other algorithms, something like that, log finder or object tracker. But at the very basic level, which is low level vision, this is what different. Thank you guys. I hope that was enjoyable.